let's start doing mathematics. The first chapter has the very simple title, Sets and Numbers, because this is what I want to talk about. The first section will be basic set theory, so we will discuss sets and their most elementary properties and start very generally. As I've told you, we want to kind of rebuild all mathematics from the beginning. And then define everything rigorously and derive everything from a set of axioms and so on. But there is one term that kind of needs to fall from the sky and that we don't really define in this way, namely the notion of a set. And I've written here, this is almost a quotation from work of Georg Cantor, who was a very important set theorist, very, very famous mathematician from 1845 to 1918, and who was a professor for mathematics at the University of Halle, which is only 35 kilometers about from Leipzig. So from the neighborhood. Okay, and this is the kind of the informal definition I want to take. So I put this here in these things, these symbols whose English name I've forgotten. Parentheses. Okay. Parenthesis. A set is a well-defined collection of distinct objects and objects of our perception or of our thought. These objects are called elements of a set, of this set. So, two crucial terms are here, well-defined and distinct. What does this mean? Well-defined. This means if I have some object of thought, or some, speaking in a very abstract general way, for each object of thought or perception, we can determine and uniquely determine if this is an element of the set or not. We can clearly say for a set, this lies in the set, this does not lie in the set. Okay, we can determine if it is in the set or not. Okay, this is what we refer to when we say well-defined. Then distinct objects. This means every object is only once in the set, once as an element. So we do not have multiple copies of the same object, so to say. So every element occurs only once in the set. Okay, this is quite vague, but I think most of you should have a good notion of a set from school. So this is, I'm not going to set theory because this is a lecture for physicists and not very foundations of mathematics or whatever. So this is definitely enough for all of you. Okay, this is blocked, this is needed, so I need to continue here. Just some notation. Okay, we write x in M. This means the object x is an element of the set M. And if we have some object which is not an element, we just write almost the same, but we just write this line through the element. So this should mean the object x is not an element of M. Okay, and the standard way to write sets that every one of you has seen before is in these special brackets. I don't know the name of these brackets in English. I really looked them up until the next video. That's quite embarrassing. Anyway, this is what we write. We write these special brackets, and in the middle we describe the elements in some way. So where the dots are here, this should contain a description of the elements of the set. So this is a set containing the elements described by these dots. And there are several ways of filling in these dots. And I will, we will see two different forms basically. First of all, the very first example. Okay, all theorems. So as you will see, a math lecture is usually very, very structured by examples, theorems, definitions, remarks, and maybe other things, and I will try to do consistent numbering. So this is example 1.1. The next object will appear here. This is, give you a spoiler, it will be another example. This will be 1.2. Then we will have definition 1.3 and so on. So I will try to use consistent numbering. And the numbering should coincide with the lecture notes. Okay, so very simple. The very first set we study has just 3 elements, 1, 2, 3. We write this in commas. So this is just a set with 3 elements. This is one way of writing this. Then I describe some sets which you already know from school, namely first of all the set of natural numbers. And here I use this symbol with a colon in front of this equality sign. This means the left-hand side is defined as what's coming on the right-hand side. So we define the thing that's next to the colon as what follows. And the natural numbers, this is just the numbers 1, 2, 3, 4, and so on until infinity. So we will give a more formal definition of these things now, because now we haven't talked about numbers yet, but I will just use these sets here to have some examples, because otherwise we can't do anything basically. So these are the natural numbers. The set of natural numbers, of course. Please be aware, in this course, 0 is not a natural number. This change, I think this is the more common convention that I'm using, that the natural numbers start with 1. Some others might also start with 0. So if you're using textbooks, lecture notes, whatever from other authors, there might be a slight difference. So please be careful with that. Then we have, as the next thing, a set of integers, z, with this double dashed z. So this is now the set of numbers we get 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on, so all the negative numbers. This is the set of integers. And we can also, for example, use other ways of describing set. For example, the set which I call 2z. This is the set of even integers. So 0, and then we get 2, minus 2, 4, minus 4, 6, minus 6, and so on. These numbers we call even. So these are just examples of very, very simple sets. These sets have all something in common, at least the last 3 of them. We just list the first elements and then ... and we are confident that the reader will then be able to figure out what's coming there. Of course, this is a bit imprecise because, technically, very theoretically, there might be some changes and we rely on the intuition of the reader. So there's a nice way of describing sets a bit more carefully. And this is another possibility of describing them. The so-called propositional notation. This term is not very important, so you don't need to keep it in mind. You just need to keep in mind whatever how this works. Namely, we start with some logical statement, some logical proposition. Which is making some statement. So technically what this is not important, but just some logical statement, some statement about some object X. Logical proposition about the object X. And then we write the following. The set of all X such that, we have this vertical bar here, A of X. This is supposed to be the set of all X for which this logical statement is true. The logical statement, I mean, we only have true or false as possibilities, for which A of X is true. I will give you an example in a second. And another way one uses to describe things here is also to add some, we restrict to some X in M for some given set M, and we only restrict to those X which lie in the set M for which this is true. So this would be the set of all X in M for which A of X is true. So this is basically restricting to some special set. So this looks very theoretical, but as soon as I will give you some examples, you will figure out what's the idea. So example 1.2, namely, first of all, let me use this one. We take M1 is defined by taking all x from z, so all integers, such that x is bigger than 5. Okay, not a very fancy set, but anyway. Now the logical statement is here that x is bigger than 5. And we need to find all those x for which this is true. And of course, if we use these dots again, this would be the set which is just 6, 7, 8, and so on. So this is a clear, clean way of writing this set without using these ugly dots. Okay. Second example, M2 is supposed to be the set of all x in z, such that 1/2 x is in z. So 1/2 of the number is an integer again. And if we take a sharp look, this is nothing but the set 2z from above. All even integers here. So again, this is a clean way of not using dots and having a really decent description here. Okay, let's take a look at another example. We take the set of all integers such that 3x is equal to 2. As we know, this equation is not fulfilled by any integer. So the set of all these things for which this is true is empty. There's no element inside. There's no such number. And this empty set is denoted by this symbol, as you will probably have seen. If we have students from Norway, they will also use this for occurring in some words, but here it's only the empty set. So this is the empty set. The set which does not have any element. Okay, containing any. I can't write anymore. Any element. Okay. Yeah, these are first examples of sets and of this propositional notation. Yeah, let me just quickly erase the blackboard. Okay, usually I will edit out when I clean the blackboard because there's no point in, this is the running water here, because there's no point in watching me clean the blackboard for 2 minutes or however long it takes. But I want to show you the famous German art of blackboard erasing. Namely, we use water and a lot of it. I think in most countries you use just a dry sponge, while in Germany it's very common to really clean it wet and watery because it's much cleaner afterwards and much more readable. Oh, that doesn't sound well. Whoops. I think there's also people who have a much more systematic technique of using the sponge and erasing the things systematically. Okay, now that the blackboard is wet, we of course can't write on it, and instead of waiting for half an hour to dry, we have a fancy high-tech tool, namely this one, which is called Abzieher in German. I have no idea about an English name, and we just pull it over here, so the water is running to the side and to the ground. And as you can see, we go left to right and left to right and left to right. And we're ready to go. So, after these examples, some more notation. So, I would say the material in this section is not very hard, so it's really to get used to this abstract way of thinking. Definition 1.3. Okay, that M and N use sets. So we start with two sets. And we want to define, first of all, the union of two sets. This is defined as the set of all x, such that either x is, or not either, such that x is an element of M or x is an element of N. And please keep in mind, if we use the word or in mathematics, it means it could also happen that both is true. So it does not mean either or. Right? It could be an element of M and an element of N. So this is the union of M and N. Okay, second set we want to study is the intersection M, and now this letter here upside down, this symbol here upside down. This is defined as the set of all x, such that x is in M and x is in N. This is the intersection of M and N. And third set we want to study M without N, this is what we say, is the set of all x. So it's some diagonal bar here. The set of all x such that x is in M, but it is not in N. And this set is called the difference of M and N. Mostly we will say M without N for this purpose. And I have some sketches in here so we can see these things. Let's assume we imagine these two sets as circuits. So we consider the insides of the circuits as points. So we have two circuits which intersect, M and N, and we want to study the union. So the union is the set of all x such that they are in one of the two. So this means the union here is just everything inside the circuits. Okay, everything. The intersection, M intersected with N. This means we need those points which are in both sets, and this is this area here, which is lying in both of these circuits. Or not really circuits, but if I could draw, these were circuits. Then we want to study M without N, so the points of M which do not lie in N, and this would then be this set here. So everything in M which is not in this area which intersects with N. Very simple. Okay, so much for that. And just to do a very simple example of these constructions, we take two sets and we see that these are just formal elements. We don't talk about context, so I take a wide mixture of objects. We take M is the set which contains 1, the word tree, 17, and Leipzig. And we take N to be the set which contains 1, 2, the word tree, the number 27, and Dresden. So, two different sets, and then we can determine these three things. So first of all, the union is the set of objects which are in one of the two. So it's just the set 1, 2, and keep in mind I had said that a set consists of distinct elements. So if 1 lies in M and 1 lies in N, it only appears once in the union, because we don't count multiple copies or anything. So the union is here just 1, 2, then we have 3, and here it's the same. We have it in both sets, but we only take one copy of it in here. 17, 27, Leipzig, Dresden. Okay, now the intersection. So those elements which are in both sets, and if we take a close look, it's not that many. It's 1 is in both and 3 is in both. Finally, M without N. So everything in M which is not contained in N. So 1 and 3 are contained in here. So the difference here is just the remaining terms, remaining elements, 17 and Leipzig. And we don't care at all about these elements which are not contained in M. So this would be the very basic example. Okay. Before I go on, some more logical notation. Definition 1.5. Okay, the next aim is I want to generalize the notion of union and intersection, not to by just not taking only 2 sets, but many, many, many. So we could take infinitely many in some variety of sets, and we want to define their union and their intersection. And this requires some technicalities. Namely, just take a set M and A of X, a logical proposition, making statements about elements of M. Then we introduce the following symbol. This symbol here, it's like in capital A upside down. This means for all. For all X in M, colon A of X. This is a way of writing, and this means this logical statement A of X is true for all X in M. So we speak this symbol as for all, no? Capital A upside down. A different way of writing this, you can either do it like this, and the colon basically saying such that this is true, or another way of putting this is A of X for all X in M. So to put it behind. This is what I'm more used to and what I find more convenient later, but these are saying the same things. Okay, this is for all. Then we have one counterpart, this symbol here. It's almost like an E backwards, but with this middle dash extending a bit further. This means there exists an X in M such that A of X. So this means there exists X in M for which this proposition is true. These two objects are called quantifiers. They are from formal logic, but we'll go into detail in here. So this means every element of this set has this property, and this means there is just some element. We only know there's one. It could be many, could be only one, doesn't matter, but we only know that there exists some element which has this property. Okay, then if we have 2 logical propositions, so some logical statements, then rewrite A, and then we take a an arrow with 2 horizontal lines here to B, and say A implies B if the following is true, or if the following holds. Oops. If proposition A is true. So this does not make any claim about something being true or false. This just says if A is true, then B is true as well. So we don't make any claim about anything being true. We just say if this holds, then this holds as well. D, we say that A and B, again two propositions, are equivalent if, and right, there's also a symbol, probably already know these things. A is equivalent to B, so again this arrow with two horizontal lines, but now with tips on both ends. A is equivalent to B if A implies B and B implies A. And this means that statement A is true if and only if statement B is true. So they're expressing the same thing, or they're describing the same fact. Okay, yeah. Then again, at the end, two symbols. We use this wedge to denote the word "and" in between two logical propositions. So if we want to express that A is true and B is true, we write A wedge B. And we have a counterpart, namely the thing upside down, like a little V. This is the logical OR. So this is, we want to express that A or B means that A is true or B is true or both. So this is just abbreviating here these notations, which I will use later. Let me just give some simple example. 1.6. You can say, if Anna lives in Leipzig, just some logical statement, if Anna lives in Leipzig, then this implies that Anna lives in Germany. If we write it like this does not make any statement if Anna really lives in Leipzig or not. We just claim that if she lives in Leipzig, then she lives in Germany. Very simple. Second example, a bit more mathematical. We use a thing from before, namely if X is in the set M or X is in the set N. This was the way we defined, just without the symbol here, without this OR symbol, this is the way we defined the union of two sets. So this holds if and only if we are in the union. So this is equivalent to saying that X is in the union of M and N. So this is the way we use these logical symbols, and we will see them many, many times later on. Okay, before I proceed, I will now erase the blackboard, and this time I will edit. Okay, now we study unions and intersections of general families of sets, and by this I mean the following. Definition 1.7. We start with some set I. I'm sorry, but my capital I in my terrible old school handwriting looks like a J, but this is really an I in notation. I'm sorry for that. Let I be a set. Yeah, and we now take Mi indexed by I in I be a family of sets. This just means, family of sets. We just take for each I in this index set, this is why we call it I, in this set I, for each such I, we take a set Mi. So Mi is a set for each I in I. Then the union, this is with this huge union, the union over I in I, Mi, is defined as the set of all objects X such that X lies in one of these Mi. If we had two, it was just, we would need to lie in one of the two. Here we need just in one set from the family. And this we can express with the symbols I introduced earlier, namely there exists an I in I such that X is in Mi. Okay, this is the union of the family Mi, I in I. And the intersection is very similar. Now we again turn the symbol upside down. The intersection over all I and I Mi is defined as the set of all those objects X. And before we had two sets and we wanted to lie in both of them. Now we have a family, so some You have many, many sets, and we want this to lie in every of these sets. And here we can use the other symbol I just introduced, namely, for all I in I, we want that X lies in the set Ni, the intersection of this family. Okay, we probably won't need these notions straight away, only later, but I want to give a, just this general description before. Okay, as a simple example, let's take n as the index set I, and this means for every element of n we take a set, and we take the following. An is supposed to be the set 1, 2, 3, and so on to n. And this we define like that for all n in n. Okay, then the union over all n in n of these an. Okay, so this means everything which is contained in one of these an. And we see that these sets become bigger and bigger and bigger and until every natural number is contained in one of these sets. So the union of them is simply n, everything. The intersection of all n in n, an. So we have to take a look at which elements lie in all of these sets. And since we only start with the set containing 1, then 1, 2, 1, 2, 3, and so on, the only thing lying in all of them is 1. So this here is the set which has just one element, namely 1. So this is this infinite intersection in some sense. Okay, a bit more terminology. I'm really sorry that I'm maybe boring you with these technical terms, but I really prefer having all the foundations in the beginning and then being able to do the mathematics without being interrupted by some preliminary stuff. If we have two different sets, m and n, we say that, I have to organize the blackboard here. We say that m is a subset of n. So this we denote by m subset n, so this symbol here, this lying u. Some authors also use this term, this notion with this dash under here. This is supposed to mean the same thing, so I will use this subset symbol, but please don't be irritated if you find this symbol in other lecture notes or books. Subset, if every element of m is also an element of n. So everything which is in the smaller set lies in the bigger set. Is an element of n. Okay, so very simple notion. B, we say that two sets m and n are equal. And I think every one of us has a notion of what equal should mean in this case. Okay, and this we denote then by using the same equality sign as for symbols, denoted by m equal to n. If m is a subset of n and n is a subset of m. So we have this, we have these two relations. So everything that's contained in the one is contained in the other, and vice versa. If m is a subset of n, and if it's clear which big N we are referring to, then we introduce some notation, namely m with an exponent c. This is supposed to be an abbreviation for the set n without m, and this set is called the complement of m in n. So everything that remains if we subtract m. Complement of m in n. Okay, finally, this fancy P of m, this is supposed to denote the set whose elements are the subsets of m. So the set of all A such that A is a subset of n. And this set is called the power set of n. Okay, the set of all subsets, and we just, yeah, I would give a quick example before one remark. Remark 1.10. In general, if we want to show, and we will prove it many, many times, that two sets are equal, so strategy is maybe a bit over the top, so strategy in parentheses, to show that two sets are equal, it often makes sense if we have complicated sets that we show these two inclusions, M, so this is called inclusion of subset. M is a subset of N, and N is a subset of M individually. So it sometimes really makes sense to keep these things separate and prove them one after the other. Oh, forgot one thing here. Just notation. We also have this symbol the other way. We write N. We just mirror this symbol here. And this is just by definition the same as M is a subset of N. So we can also do this, write this in the reverse way. This is just notation. Okay, now for the example. So very simple example. 1.11. We start with a very simple set, namely we take this set which contains 1, 2, and 3. So what is the power set of this thing? So what are the subsets of M? Okay, first of all, every set is a subset of itself. This is clear from the definition. Yeah, every element of M is an element of M. That's trivial. So the set itself is contained in there. So 1, 2, 3. And now we do this systematically. We now take subsets which are not the whole set of M. This is sometimes also called proper subsets. So subsets with fewer elements than this. This has 3 elements, so let's take all subsets with 2 elements, and there are 3 of them, namely the set 1, 2, the set containing 1, 3, and the set containing 2, 3. These are all subsets with 3 elements. Now the subsets with 1 element. This is just the set containing only 1, the set containing only 2, the set containing only 3. And now we're almost done, but we're not done because one set is missing. The empty set. The empty set is a subset of everything. So this always needs to be contained in the power set, and now this is the power set, a set of sets. And also for, just as an example for the complement, for A, just the set 1, 2 as a subset of M. We have that the complement of A in M, this is a big set without this, so this is just the set containing 3. Okay, in the next theorem that, so we do the first real theorem here, but I have to erase because that theorem is a bit long. See you in a moment. Our first theorem, and it's the first of many to come. This first theorem is actually not that exciting, but it's necessary. Namely, we want to just do for our bookkeeping records, state some properties of sets and of unions and intersections. I take 3 sets, M1, M2, M3, which I use to formulate these properties. And basically, it's just a list of properties that intersection and union have. First of all, part A, this property is commutativity. You will figure out later why this makes sense. So this is just, first of all, the name, how it's called. M1 union with M2 is the same as the union of M2 with M1. So the order is unimportant. This is almost trivial. I mean, if you write both definitions down, it almost stands there. So there's not much to prove. And the same for the intersection. M1 intersected with M2 is the same as M2 intersected with M1. Okay. Not that fancy. B, associativity. This says that the order of taking unions intersections doesn't matter. Namely, if I first take the union of M1 and M2 and take this new set, and then take the union with M3, this is the same as if I would do it the other way around. If I would first take the order of M2 and M3, and then take the union with the set M1. So the order is irrelevant here. And the same for intersections. So I just write here, same for intersection just by changing the symbol. Also, the order of taking intersections doesn't matter. Third property is a bit more interesting, or a bit less obvious, I would say. Distributivity. Namely, two statements. First of all, if I take the union of M1 with the intersection of the two subsets M1 and M2 and M3, this is the same as taking the intersection of the union of M1 and M2 with the union of M1 and M3. And secondly, the same holds with exchanging the symbols. If I take the intersection of M1 with the union of M2 and M3, this is the same as the intersection of M1, the union of the intersection of M1 and M2 with the intersection of M1 and M3. Not that obvious, takes a little time to think about, but I will say a bit this in a moment. And finally, the so-called De Morgan's laws. I don't know if it's De Morgan, probably the guy is French, so it's De Morgan, but yeah, anyway. Namely, if we're in the situation that M1 is a subset of M3 and M2 is a subset of M3. So we have one big set, M3, containing the two others, then we can talk about complements, and this is what these laws are about. Namely, if I take the intersection of M1 and M2, and then build the complement of the resulting set, it turns out that this is the same as taking the union of the complement of M1 with the union of the complement of M2. And the same holds with the operations exchange. If I take the union of M1 and M2 and then take the complement in M3, this is the same as the intersection of the two complements. Okay, this is something I urge you to draw a set diagram like I did before with these things, and because this is easiest to see in a diagram. Where are these complements? How do they look like? And where are they? And so maybe yeah, take your time and then draw this and try to think about this in this way. Okay. Actually, this is a theorem, and since this is a mathematical lecture, we should every theorem needs a proof, and everything I'm claiming will be proven, except here, and except a few other spots, because this is really a long computation, which is not that exciting. So we'll only prove one part of it, and just can tell you the remainders are, the remaining parts are shown in the very same way, so by analogous arguments. So you're encouraged to really work out your way through the proof for everything else. And I will just prove the first equation of part C. So the proof of C.1. And now I will follow my own advice. I've said that the equality of two sets can be shown by showing that one of them is a subset of the other, and for both directions individually, and this is what I will do. And this is often abbreviated by just starting by saying, okay, this is now the part where we show the left-hand side is in the right-hand side, and the other part will then be the other symbol here. We will see momentarily. So here we want to show first that M1 and with the union of M1 with the intersection of M2 and M3 is contained in M1 union M2 intersected with M1 union M3. And if there's a claim that we haven't proven yet but want to prove, there's a nice way of indicating this. We just put this exclamation mark over this thing, over the relation we want to show. So this just means this is what we want to show. So just as a reminder. So we start like this. So subset means every element of the right-hand side is element of the right-hand side. So we start with an element of the left-hand side. Fx is in the left-hand side, M1 union with the intersection of M2 and M3. Then by definition of the union, we know that x is contained in M1 or x is contained in M2 intersected with M3. We will now, it could also be that both is true, but we will now treat these two cases and show that in both cases we will get that it's in the set on the right-hand side. First we assume that x is in M1. Then it follows, so this implies that x is in the union of M1 and M2, which is trivial because we just increased the set here. And it also is true that X is in the union of M1 and M3. We just increase the set again in a different way. But if it's in the intersection of these two, this is by definition, this means, if this is in this union, by definition, this and symbol then means that, so it's in both, so it's in the intersection of the two. So X is in M1 union M2, intersected with M1 union M3, and this is what we wanted to show. So this is in this case. Now let's consider the other situation. Assume that X is in, if this is not true, we need to study the other case, is in the intersection of M1 and M2 and M3. So this means that X is, just by definition, X is in M2 and X is in M3. This implies, and again we can increase the sets. If this holds, then surely this holds, simply just increase the set. And the same thing here. If X is in M3, then it's definitely in the union of M1 and M3. And these two together, again, imply that X is in the intersection of these two sets, what we wanted to show. Oops, sorry, a bit small, still readable. So in both cases, we have shown that this holds, and so this shows actually what we wanted to show. We have shown that every element of this thing is contained in the right-hand side, which concludes this direction. So for the other direction, this is what we denote like this. So with the other symbol, we now want to show that the right-hand side is contained in the left-hand side. So we need to show M1 union M2 intersected with the union of M1 and M3, that this is contained in M1 union with the intersection. Okay, now we take an element of this set here, so that X in M1 cap the union M2 intersected with M1 union M3. So this means that X is in M1 union M2 and X is in M1 union M3. So now there are multiple things that can happen. So we first again assume the case that X is in M1. Okay, if this happens, this is almost, then it's clear that because this is just increasing M1, then it directly follows that X is in M1 union with M2 intersecting M3. So then we're done, because there's nothing to show. Now, what happens if we're not in M1? If X is not lying in this set? Because this holds, then here we know, since it's not in M1, it has to lie in M2, and here we know it has to lie in M3. So X lies in M2 and X lies in M3, and this just means, written as sets, X lies in the intersection of M2 and M3, and this implies, if we just again make the set bigger, it's in the union of M1 with the intersection of M2 and M3, and this is what we wanted to show. So, yeah, this is what we wanted to show. We have shown that in both situations that can occur, we get that X is contained in the right-hand side if it's in the left-hand side of this equation here, and so of this relation here, and so we're done. And if we have proven a statement, so let me just add, this shows the claim. If we end the proof, we always do it by making this small box in the end. This is a symbol which means QED, quod erat demonstrandum, so this means end of proof, just to give it some structure and to see where things start and end. Okay, yeah, the other parts of the theorem I will not prove, but they are worked out in a similar way, but as you can see, this will get quite lengthy, so let me skip this, and I have to erase again.